I'm the operator with my pocket calculator.
Yes, ladies and gentlemen, I also would like to welcome you to the... Not loud enough? Okay, I'll try to read louder, to speak louder.
I don't think the micro is on.
No, I think the micro, there's no speakers, it's just for the, for the video.
Very briefly, we don't have here any audio equipment because I thought it's not necessary in a room size like that. We have here a recording of the sessions and the presentation. And just for this recording for our Spanish friends, we have the micro. So.
Okay, can everybody understand me up to the
I would make a
last
final
time? Okay, thank you.
final adjustment. Okay.
Okay, I'm very glad to have the honor to open today's session with the first presentation for the IM 2017. It is not only the opening of the international meeting, it is also an opening of a secret which is below, which you can see below this red scarf. It is the presentation of an instrument which the world has never seen before. It's an own construction, and we will open this soon. You will participate in the world's inauguration of this instrument. But before, I will have to give some background information so that you understand what is the idea of this instrument and what is the process of or how is the process been of developing this instrument. To understand what is below this scarf, it is necessary to know a bit about my background. Some of you know me already from previous meetings, others not. I'm a civil engineer with a specialization in hydraulic structures. And that is the field of interesting also in collecting slide rules. So I'm collecting slide rules for all these type of structures or calculations for these structures, hydromechanical calculations finally, related to structures. There are very many, there's a manifold slide rules to solve problems in hydraulic engineering. Some very specific specimens I presented in previous meetings, the last one in Italy last year, or at the meetings of the German collectors I also presented 2 or 3 pieces. And I'm not going to do that again, but it is just as a background information for you about what I've built here. Yes, with the time, the idea came up, would it be possible to build an instrument to calculate with water instead of calculating the properties of water with slide rules, so just to turn the tables on. That was the idea. Could we do it otherwise? So not use the slide rule to calculate the flow, but use the water to make any calculations. So you can say the idea was to build a hydromechanical calculator. Just let me have a small look on my papers. Yes, so this idea didn't go out of my mind, and one day I decided, or I started with some survey, some investigation. Does such an instrument already exist, or did it exist already in the past? Before inventing such an instrument myself, I wanted to know whether it existed already. I did not find any instrument to calculate with water, but what I found are many applications for measuring with water, and some of them I will just present you very briefly. So one application every one of you knows is the water level or spirit level. Every one of us has used such an instrument already. So we can talk about daily use or daily, not calculating daily measurements with water. And it is also very presumably that already the ancient Egyptians have used the property of the water to build horizontal surfaces and have leveled the base of the pyramids by water-filled trenches. Another application for measuring with water are water clocks. Again, already the ancient Egyptians, they have used water-filled receptacles with a small borehole here at the bottom where the water could flow out, and with the time the water level was increasing, and that was a measurement. By that they could measure the time more or less exactly. The systems have been developed later by the Romans and the Greeks, and they have built very complex water clocks with a lot of gimmicks and special effects also. On the right photo you see a water clock standing at the Europe Center in Berlin. It's called the Clock of Flowing Time. It's very interesting to watch this clock. Don't know, some of you may have seen it already. You can see there are a lot of videos, bowls filled with water, and this picture has been taken. Who can read the time when this picture has been taken? It was some minutes before 5. So you can count here the full hours, 1, 2, 3, 4, almost 5. And these are the minutes. Each bowl represents 2 minutes. So it's almost, the hour is almost completed. 2 or 3 minutes later, everything emptied again, and it started again filling. So quite nice instrument. Another application of measuring with water, or using the water for measuring, is said to this old man. You all know him. It's an old Greek, Mr. Archimedes, and it is said that while taking a bath, he found out that it is possible to measure the weight or the volume of a weight of a swimming body or the volume of a sunken body just by the displaced water. And it is said that he used that to measure the specific weight of gold, for example. Maybe it's an anecdote, maybe it's true, who knows. But it is still called the Archimedes law. Last example I want to show you is the first example, or the only example I found, which you could call like a computer. It's like not really a computer, but it can calculate just one. This instrument can carry out one calculation. You know the law of Pythagoras, so that the sum of the square of the two smaller sides of a rectangular triangle corresponds to the square of the large side. And let me see whether it works. There's a nice application. You can find that under YouTube. Okay, we start. And very simple, we can carry out the calculation. A square equals to, no, C square equals to the sum of A square and B square. And otherwise. So that's a nice instrument, nice. You can carry out a calculation, but only one calculation. You cannot change it, you cannot carry out other calculations. So it was not what I was looking for, but it was at least a first idea. Okay, as a result, I can say it was necessary to develop an own instrument. And so I started with my investigations. Oh, still, sorry. Okay, let's stop it. Okay. Okay, so I started investigation. I wanted to build an instrument, a computer based on the fluid or water, which is easy to understand, it should be easy to handle. It should be multifunctional or programmable, so I wanted to carry out more than one calculation with it. It should be transportable because I wanted to present it to you today here. It should be economical and sustainable as far as possible. Sustainable, it should not use any energy, for example. So I started with very complex calculations, hydromechanical theories to find out what would this calculator have to do, which calculations would I have to, what did I want to solve with the calculator. And you see me here thinking, this was the beginning of the design phase. Very soon I noticed that I could not invent this instrument myself. I needed more brain capacity, and so I involved all my students. They supported me, they investigated slide rules, how they worked, and helped me in developing this instrument which you see here below. Now still you don't see it. I had to carry out laboratory tests to find out the exact behavior of water and to find the best mixture of the fluid for my instrument. And so step by step I started designing, I started preparing sketches. Many ideas were born and they had to be rejected again. And after the time, step by step, the best idea came out. And after a lot of sleepless nights and uncountable cups of coffee emptied, it was finally done. It was done, and the instrument has been designed, and now started the building phase, the construction phase. I'm not going to present it, but we are not at the moment where the world will see for the first time the so-called hydroculator. Hydroculator, you can read the name, just here you can read it, is the abbreviation for hydromechanical calculator. Okay, ladies and gentlemen, be prepared. Hope it will work. Prepare your cameras, yes, let's welcome the hydroculator. Okay. Okay, let me see. I think we should maybe switch on the light now. Jorge, could you switch on the light? Okay. You will find it. I want to test this instrument with you. I want to carry out some calculations with you, but before we are carrying out the calculations, I will just explain how the instrument works and how it is built. And therefore we can open it again, but this time virtually. This is the hydroculator. Well, how is it built? So it is composed of 3 cylinders. The middle one is the so-called full reservoir, whereas the left and the right one are called the reactors. They are used for the calculations. Each reactor disposes of a display. And these displays are changeable. So we can change it from one display to another and thereby carry out different calculations. The program code is written here. So in this example, we just see the program code for carrying out multiplication and divisions. The system is operated with green and renewable fuel. We have here above, below, we have the control center. That is like the motherboard for a computer. It's our control center where we will carry out the calculations. And we need some energy, some power cell, which is air pressure in this case. Okay, are you ready to start? then we will try to carry out calculations. First operation will be who can calculate that by mind? This is point. Well, it's 3 minus 0.6. Like this is easier. And then you see 9 minus 0.36 equals to 8.564. I wrote something different, but that's not correct. That's the correct solution. Okay. How can we do that? We are going to fill the both reactors up to the 2.5, the one up to 2.5, the other one 2.4, sorry, the other one up to 3.6, and that's the first step we're going to carry out now. The full tank is filled with water, and now I will start the operation. So 2.4 on the left side. We open valve number 1 and valve number 2. And wait until the water
Oops.
2.4. I will show you later with the camera. Now we fill up the other side until 3.6, and I think we need some energy for that. Well, here's my power cell. Just some pressure. 3.6. Okay. Okay, that should work. Let me see. Let me see whether I can show you with the camera that you. Okay, let us see. So we have 2.4 and 3.6 on the right side, correct? Okay, let's start the operation. Now we will have to transfer the water from one column to the other one. We'll open these two valves. And again, we need some power. And we have to empty the left column and up to or down to 1, down to the lowest mark. Okay, let's read the result. Okay, here we are, emptied. Let me see. What is the result? 8.6 and something. Perfect, isn't it? It works. Okay. Okay. We're going to make one or two more calculations. The next calculation I want to carry out with you is (8.64) divided by the square root of 9. Okay, everyone can calculate the square root of 9 by mind very easily. That's why I choose this example, so we can calculate it by mind. But we'll see how the calculator is doing that. So first by mind, what's coming out here? Who can do it? Oh, not so easy. 8.7 by 3 and then 288. Very good. First one. That should come out. How can we do it? Now we'll change the program code. So the new code on the left side is a square, x square, and on the right side we have the normal logarithmic scale. Sorry, like that. So we want to divide by square root of 9. So let the flow, we will let the water flow from the right column to the left column until it fills up to 9. Now looks like we need some more pressure. Okay. Should come out 288. Let's see. First on the left side, to be convinced. This is square root of 9, or this is a 9, so it's square root. On the right side, we can read the result, and that is 2.8, almost 2.9. 88. I would say it's exactly 88, isn't it? Another proof for the functioning. Okay, the last calculation, and then I think you are all convinced that the system works. Now we are going to multiply ja, ich habe hier den roten. Ja genau, ich wollte wieder abwechseln.
Okay, versuch's einfach.
Nee, dann nehme ich den roten. Ist okay. 2.88. The square of 2.88 multiply with 11.7. That's not so easy to calculate by mind. So I will just help you. The square of 2.88 is almost 8.7. 8.3. And again, you can recognize the binomial formula. We can calculate it which is about 100 minus 2 point, I think it's 89, isn't it? 89, yes. Just had to. So it's 97.1 more or less. 97. That should come out. How can we do? We change our programming code again. I will change this scale and use another square root, square scale. And the first thing we can read on the right side is the square of 2.88, which is 8.3. Just by changing the scales, very simply. Okay, now we want to multiply with 11.7. That means I will have to fill up this reactor up to 11.7. We will have to use full from the tank. And some pressure. Nothing is working without energy. Okay, 11.7. Bit too much. Okay. Let me see. It is more or less 11.7. Okay. Carry out the calculation, close this valve, open this valve and that valve. And carry out the operation. Okay, last result. I emptied the left column and the right column should give us a result, which is 97, well, it's not almost between 97 and 98. Maybe you can see it better like that, yes. Well, I was maybe not careful enough by carrying out the calculation. So that's the principle of the hydroculator. You can prepare any scale as you like a normal slide rule, of course, and principally you can carry out any calculation that you can carry out with a slide rule. Of course, it's taking much more time. But the idea of the calculator or the this hydroculator is just to have another, just to, how to say, to demonstrate this principle of of logarithmic calculations by a very diverting manner, and maybe I can also use that to bring the principle of slide rules or interest the students for the principle of slide rules with that. Okay, there we are. That is the end of the presentation, and I thank you for the attention.
Said differently, Shakespeare's plays. That's the plan for next year. When? Well, it's always sometime in September, at a date very similar to this year, namely 21st and 22nd of September 2018. So everybody, please take out your calendars, your agendas, and write it down. So, what? Yeah. So, and again, we have a theme, and if it's Shakespeare's plays, it has to be something with that. So it's from sonnets to sums. Okay, you know what to do. Everybody, take out, go to the bookshop, read your Shakespeare again, find good quotes to make nice presentations. Yeah. Everybody has to do so. So you recognize in the quotes your presentation, please. Yeah, very. But this it's at the Stratford Hotel. The Brit and the English have also a certain tradition, namely to make a display that is to call out and for people and bring along their specific thing for this theme, for display, and that is early British rules and secondly long scale rules. So again, dates we need, a certain notice to intend the paper so that they know what's going on, deadlines and all that. And the important thing is they're really hurried to have those things, everything ready. You can read that all on the website. But first, I have to give a warning or an information. First, there is this place, Stratford-upon-Avon, south of Birmingham. That's the place. But there are several other Stratfords in Britain. Please, Stratford upon Avon. What else is on the map? There is a place called Milton Keynes, which is actually not meant, but a place nearby. Actually, the place nearby is something about here. Yes. Where we already have been in 2012, namely Bletchley Park. And this is just a reminder, anybody traveling to Britain, that they have there the National Museum Computing, and of course there's also a display by the UK SRC, by the UK slide rule collector. So go along there, have a look, even more, and if you've been there, just a refresher, because lots of that is refreshed, because many things there belonged to Colin Burns and were sold a year ago. So, plan your trip. This is a view of the hotel, and most important is, next to the date you wrote in your notes, that you write down this web address, this URL, yeah, UKSRC or UK, you should know that, and IM 2018.